everyone, this is the part 2 of my most versatile power bank build. In the last part, we finished the main control board of the power bank, and I also showed you all the new features and functions that this power bank has, so make sure you watch the first video first. Now, thanks to all of your support and suggestions, I now plan to host this project on a crowdfunding campaign with an updated design based on all the feedback and suggestions. So stay tuned as it is most likely to happen in the near future. In this video, I will go over the overall construction and assembly of the power bank, and I will show you how to make various modules to expand the power bank's functionality. I will also include a few blank module templates, which you can modify with your own 3D design software to make your own module suited to your own need. As for always, all the links to the design files, the code, and the diagrams are in the description, and this development version is completely open source, which means that you can modify it and improve on it however you like. And this project is also sponsored by JLC PCB, which you can order 5 PCBs for just $2, and thanks to their SMT assembly process, which dramatically reduces the hassle needed to create the power bank control PCB. Furthermore, due to all of your suggestions, I am also working on a fully integrated circuit, which further eliminates the need to purchase separate modules. Check out part 1 for building the main control board and how to place an order for JLC PCB. With all that said, let's get into the final assembly process of the power bank. The first thing you are going to need is all the 3D printed parts of the power bank, and these parts have to be printed out of either PETG, ABS, or other high temperature plastic, as the internals and the battery of the power bank can reach well above 60 degrees. Now get the top lid of the power bank and push the LED ring cover into it. This part has to be printed out of either white or transparent plastic, as light needs to pass through this part. Now use the soldering iron at low setting, carefully melt the plastic and fuse the two pieces together. Now get the WS2812 LED ring and place it into the indent of the LED ring cover. Then add in the wireless charging module and desolder the coil. Now cut thin pieces of nickel strips and wrap them in Kapton tape, and solder the nickel strips to the output of the LED ring, and link the coil to the wireless charging module with the strips also. What we are doing here is creating low profile wires, so the battery pack can easily slide in and out. Then, solder 24 gauge silicon wires to the end of the nickel strips, and then connect the two grounds of the LED and the wireless charging module into a single wire. Then, get a can that is made out of aluminum, then cut a piece just like the indent on the lid, and glue it into the lid using the thermal glue. The aluminum sheet acts like a heatsink to cool the LED and the coil, so they don't overheat even after prolonged use. Also, bend a piece of nickel strip like this, and thermal glue it onto the ICs of the wireless charging module. This also helps with the heat dissipation. Before installing the dot matrix display, add the 3D printed buttons, and glue it in place using superglue on a corner tab. Now, get the 8x16 LED dot matrix display, and solder the wires behind the connector. Lower the matrix onto the lid of the LED and secure it in place with M2 screws. By now, you should have a set of 4 wires from the LED matrix and another set of 4 wires from the LED ring and the wireless charging module. I added Molex connectors to them to make the assembly easier, but this is optional. The next step in the assembly process is for the power bank body piece. First, add a piece of aluminum sheet from the can onto the bottom of the electronics area, and cover it up with a piece of silicone thermal pad. This is optional, but it will help with the heat dissipation of the power bank. Then get the control board. I forgot to mention in the previous video that it is best to put thread locker or thermal glue onto the nuts to prevent them from becoming loose. With that said, lower in the control board and secure it in place using the 2 screw holes on each side, and then locate the other 2 screws on the buck boost converter and secure them in place using short M3 screws. After putting in the control board, carefully slot the MR30 connector onto the battery side. Then secure the temperature control switch next to the inductor of the buck boost converter and cover with tape and thermal pads. Then, get the lid and connect the Molex connector to their respective connectors. Carefully close the lid and clamp down on the MR30 connector for the module. Next, screw in the lid with a screw on the top right corner and 2 extra holes inside the battery pack compartment. Then, get the end clamp and snap it onto the end of the power bank. Then add on the side shields. Next, screw on the I/O shield. Optionally, you can print side accents from whatever shiny filament you like and glue it onto the power bank. And with that, the power bank main body assembly is now complete. You can test the power bank by going through the checklist, or just plug things in and test its functions. Now, let's move on to making the different modules, and I will briefly show 2 modules that I think are the most useful. They are the DC to DC converter module and the DC to AC converter module. Now, as a warning, these modules can put voltages that are dangerous or not compatible to your device or your body. Always use less expensive devices for checking before plugging in your module to your laptop or something. First, I will go over the DC to DC converter module. This module changes the voltage of the battery to 5 to 40 volts, which is useful in powering laptops, cameras, and any other DC devices that is less than 120 watts. The diagram for this DC to DC voltage converter module is relatively simple. It is a DC to DC buck boost converter with its potentiometer moved to an adjustment knob so its output voltage can be easily adjusted, along with a mini voltage meter connected to its output for measuring the converter's output voltage. And there is also a voltage regulator, along with a normally open temperature switch that automatically controls the cooling. So the first thing you are going to need are the 3D printed enclosures. Then, get an MR30 female connector and solder on 3 18-gauge wires to it. Then, insert the connector onto the side of the module while making sure the VCC pin is facing the top, and superglue the connector in place. Next, attach the output of the buck boost converter to an amp and voltmeter, and then connect the buck boost converter to power and short the output. This will make the buck boost converter go into constant current mode, and then adjust the current limit until it is around 6 amps. Next, desolder the potentiometer from the buck boost converter and solder longer wires to it. Then save it for later as we move on to the fan and automatic cooling system assembly. You will need a 12V 25 by 7mm fan, a 50 degrees normally closed temperature switch, a 12V voltage regulator, and 2 10 nanofarad capacitors. And all you need to do is to solder the components according to this diagram. And after soldering the circuit, connect it to power and heat up the temperature switch. The fan should start blowing. Next, attach a DC jack to the output of the buck boost converter, then slide in the potentiometer to its holder and glue it in place. Next, get the adjustment knob and carefully push in a small piece of nickel strip. Then, trim the nickel strip until there is just a tiny amount sticking out, and push the knob onto the potentiometer and make sure the nickel strip matches up and can turn the potentiometer. Next, add in the buck boost converter and solder the potentiometer wires back to its original pads. Next, wrap the temperature switch in Kapton tape to prevent it from shorting anything out. Then connect the ground of the cooling circuit to the ground of the MR30 connector, and do it likewise for the positive terminal. Slide the fan into place and thermal glue the temperature switch onto the inductor of the buck boost converter. Next, glue in the DC jack to its socket, and then solder a voltmeter in parallel with it. Screw in the mini voltmeter on top of the case, and then slide the top of the case onto the converter body and secure it in place with M2.5 screws. Add in the I/O shield and also secure it with screws. Now, you can plug it into the power bank to see if the voltage adjustment works. Then you can begin plugging in DC devices to ensure stability before moving on to more expensive equipment. Now moving on to the DC to AC converter module, it is relatively the same idea. Although for this version, I can only find 12-volt inverters that are small. So this means that you will need a step-down converter to convert the voltage of the battery to 12 volts. Anyways, you will first need the 3D printed pieces of the inverter module. Then, glue in the MR30 connector onto the side just like the DC module. Next, get the DC step-down converter. Connect the DC-DC step-down converter to power, and then adjust the potentiometer until the output reads 12.6 volts. Then, I modified the DC to DC step-down converter to make its footprint smaller by replacing the heatsinks. Just use any heatsink that is thinner than 8mm. During testing, I found that heat dissipation is not a big issue. For the AC module, bend 2 pieces of nickel strips, then cover the back with tape, then thermal glue it onto the 2 MOSFETs on the side. After the glue is dried, solder the output of the DC to DC step-down converter into the AC module. Next, slide both modules into the case, and solder the output of the MR30 connector into the input of the DC to DC step-down converter, and also solder a 100 kΩ NTC thermistor between the thermistor pin and ground, and glue the thermistor to the step-down converter. Since there is already a connector for 12-volt fan on the AC module, there is no need for temperature control circuits. Just simply plug in a 25 by 7mm fan using the included Molex connector. Next, insert the AC socket into the 3D printed I/O shield and glue it in place. Then, trim the sides until it is flush with the side. Next, carefully plug the AC connector in, close the lid and secure it in with M2.5 screws. And secure the I/O shield in with 4 M2.5 screws. Now, plug it into the power bank and test out its functionality. Since this is the modified sine wave converter, I do not recommend using it with any inductive load such as fans. And that's it for the AC converter module. If you have any other questions regarding the operation of the power bank, just check out the documents in the design files. There is a manual for troubleshooting and the operation of this power bank. And that is it for this version of the power bank. At this point, I'd like to give a huge thanks to all of your suggestions. Please keep them coming, as they will help me to improve on the version 2 of this power bank, which I am currently designing. This version, the circuit will be fully integrated, the module connection will be simplified, and the LED ring will be fully hidden, and the power bank will be eventually ready for mass production. I will post any significant updates on the community tab. If you'd like to support my work, then please consider leaving me a tip on Thingiverse. You can also like, share, and subscribe if you like my content. I thank all of you for watching, and see you next time.